So we will now welcome St. John's School, Team 6811. So your very first question is going to be a really easy one. Tell us your name and what year you are in school, and good luck.
I'm Daniel Shabib, and I'm a senior at St. John's.
I'm Eric Gao, and I'm also a senior at St. John's.
I'm Anirudh Suresh, and I'm also a senior at St. John's.
I'm Nancy Chang, also a senior at St. John's. I'm Margaret Troutner, also a senior at St. John's.
So we'll be your judges for today. Karen Bliss from Virginia Military Institute. This is Dan Connors from IBM and Ben Galuso from Shippensburg University. You'll have 15 minutes for your presentation. I'll let you know when you have 2 minutes left. I'll give you a signal to let you know that you've got 2 minutes. And then after the 15 minutes are up, we'll have about 5 minutes of questions. Please begin.
Hi, we're Team 6811 from St. John's School in Houston, Texas, and this is our solution. So car sharing is an important and growing trend in transportation, and as such we were asked to assess the viability of car sharing in several cities. In part one, we model driving demand in the US. We evaluate drivers according to their mileage and driving time and divide them into 3 categories based off of their low, medium, and high mileage and driving time. Luckily, these metrics are interdependent, which, as you'll see later, is key in our model. In part two, we apply this to car sharing. We evaluate several case-specific scenarios for customers and several business models for car-sharing businesses and assess the viability of each model in several cities. In part three, we extend this to the future by factoring in self-driving cars and eco-friendly cars into our model to assess the future viability of this trend. Now, Eric Gao will go over part one in more detail.
Now that Daniel has introduced our model, I'll go over part one, in which we develop a versatile model for car driving patterns. Our model is significant for several reasons. Most importantly, it will allow us to determine the proportion of the American populace that is in each driving category that Daniel has proposed. So, for example, we'll be able to find the number of people in the low category or low-medium. In addition, the distances and times that people drive is important data for car-sharing businesses. Also, this model will allow us to find factors that impact velocity. In our model, we have several factors and assumptions. Our factors include population density, distance traveled, and time spent. In addition, we make assumptions in our model. These assumptions include the uniform population distribution within cities, as well as we assume that we have uniform speeds across the US of similar population densities. In addition, we assume that the low, medium, and high categories are the same across different populations. In order to develop our model, we took data from the 2009 NHTS survey, in which they surveyed approximately 200,000 individuals about their driving patterns. This is a histogram of frequency versus the number of minutes that individuals drive in a certain day. And this is a histogram of frequency versus the distance they drive. We use these two histograms to develop 2 different cumulative density functions that Anirudh will go over when he finishes part one. After we developed our data, we formed these formulas. Our first one is m equals hv, which is simply distance is equal to time times velocity. Now, velocity isn't a constant. It's a function of a traffic function, which we call t. In turn, t is a function of population density, and we actually fit it to an exponential decay formula. And here is our fit for various cities in America. The x-axis is population density, and the y-axis is t, our traffic function. Now I'll let Anirudh finish part one.
So now that Eric's just gone over the expected value for the number of miles driven in a given time period, that's not representative of a population, though. There are going to be a good number of people on either side of the expected value of the number of miles driven in that time period. And therefore, we can use a normal distribution to simulate that population and represent it accurately. G of x comma t prescribes the normal distribution, and if you substitute a value t sub 0 in for t, it results in a distribution of distances traveled by drivers in t sub 0 minutes. And using this normal distribution formula, we can incorporate it with a cumulative density function, the CDF, shown in the integral, and use the integral over a range of values in time from t initial to t final. And what that does essentially is it gives us the proportion of vehicles that travel less than y miles in a given time period between t initial and t final. If we subtract this integral from 1, we get the proportion of vehicles that travel more than y miles in that given time period. So this may look like an appropriate formula, and may look adequate, but there's one critical flaw. The dt alone assumes that there's an even distribution of daily travel times, and clearly that's not true. You're going to have far more people driving between 30 and 31 minutes, for example, than people between 300 and 301 minutes. Thus, we can use the NHTS dataset that Eric introduced earlier to scale up or down the minutes, scale up or down the widths of the integrals widths of the rectangles into integration based on the relative frequencies of travel times. So again, here you can see that effect that I alluded to earlier. This is the cumulative density function of that histogram data that Eric introduced earlier of frequency versus average distance traveled, or average time spent on the road. And so the weighting factor that we use is given in that form right there. It's the CDF of that distribution at one moment minus the CDF of the distribution at the moment right before. So that gives us the relative frequency of drivers in that minute-to-minute block. We can then incorporate this into the earlier integral to give us a final equation and a final integral form, which gives us the proportion of drivers in each of the 9 categories we want to find them in. So let's move on to validation of the model. We performed a sensitivity analysis of the m function with respect to k, which was a constant in the traffic factor function fit that we created. So as we varied k by about 14%, we found that m did not vary by as much as k, or as much as k was varied. This shows that the model was not very sensitive to changes in k and was rather robust. After the 14-hour period, we also performed a sensitivity analysis of m function with respect to r, which was another constant in the traffic factor function. And we found that the model was not very sensitive to changes in r. Considering a 100% increase or decrease with respect to r, we found that the highest change with m was about 12.4%, which shows that the model was very robust. So let's move on to results. We found that 75% of drivers in the bustling city of New York fit the top left corner of the table, which indicates an underwhelming driving experience, essentially that they drove for a very low amount of miles considering the relatively extensive time they spent on the road. And meanwhile, in a city like Englewood Cliffs, which is a small suburb, you find about 75% of the population in the bottom right corner, which indicates that the population, or these population of drivers, were much more likely to drive longer considering their relatively short driving times. This is an intuitive result, as you would expect in a smaller city or a smaller suburb, you'd encounter less traffic and thus go farther. And now I want to talk about some strengths and weaknesses from part 1 to conclude this section. We found that our primary weakness was the fact that we had a lot of root mean square error in our fit for the traffic factor function that Eric brought up earlier. However, this is attributable to A, the high level of variance within that data set, and B, the fact that traffic cannot always be condensed to just population density. However, with regard to our strengths, we think our strengths make up for that and more. We found that our model is very versatile. It could be applied to any market in America, which is especially important considering the business-related context of this study. We also saw that our model experienced low sensitivity with respect to the constants k and r, and that it was extremely intuitive in its conclusions based on population density of a region. Now I'll turn it over to Nancy for part 2.
So in part 2, we were tasked with investigating the viability of various car sharing methods in 4 different cities. And one key assumption that we made was that we disregarded the effects of business implementation costs, such as the construction of car sharing stations, because we figured that after a while, the long-term profit will override any initial cost differences. So these are the first equations that we came up with. So first and foremost, profit, we decided was revenue per user minus cost per user times total usage. Usage is a function of population density and individual feasibility. And so we then described individual feasibility in terms of user price, which is a sum of opportunity cost and monetary cost. A user's time is more valuable for higher salaries, so we defined opportunity cost as the time T spent in commute weighted by the salary S. So to model user price, we created 4 realistic scenarios for how an individual can utilize a car sharing service. Most users' car sharing needs fall into generally one of these 4 categories. And so by using these scenarios, we're aiming to model the behavior of the general population. So here, let's move on to pricing. To find M in our user price equation, we researched pricing methods used by companies, real-world companies today, and we applied those to our scenarios to generate a chart of annual prices for each option. And in this chart, the bolded options are the most cost-efficient. We also had to make additional assumptions about the time lost in each option. For example, walking from your house to a car-sharing station. These assumptions are derived from actual human walking data that is available online, and we translated those assumptions then into an estimate of the additional time required for each car-sharing option. We then took those assumptions and we calculated the total time spent commuting per year for each scenario and each option shown here in this table, and this is T in our user price equation. So to find the total cost, we're going to return to our user price equation, price equals time times salary plus money. So we took the values for T and M that we just found to generate user price functions for each car sharing option and scenario. And then we plotted each scenario, all of the options in each scenario together to compare across car sharing options. In scenario 1 in particular, the lines don't intersect, and the cheapest option, which is represented by the bottommost line, remains public transportation no matter the salary. But as we can see in graph 2, as salary increases, that bottommost line in blue, which represents round-trip Zipcar, becomes the best option when the salary reaches about $150,000. Similarly, for scenario 3, 2- and 3-person joint ownership becomes the best option when salary exceeds about $100,000 per year. And for scenario 4, the free-floating car-to-go model and one-way station Zipcar Boston become the best options as salary increases. And these are real car-sharing scenarios that are available to the public right now. So we just use those to model our scenarios. So this is just the combined graphs, just to show them all together. One thing to note is that in all of these models, personal preference might render car sharing a more favorable option for the consumer than public transportation. So even though the salary cutoff seems very high, in reality it's a lot lower. But overall, as salary increases, certain options become much more feasible because the high monetary cost is offset by the time saved. So we just looked at which options are the most consumer-friendly, and now we're going to look at the options from the company's perspective. So for company revenue per user, we summed the revenue generated from monthly rates, hourly rates, new user fees, or a combination of all of those, depending on how a company decided to price their car-sharing service. And then for company cost per user, we added the cost of car maintenance and the cost of gas for one car, and then divided that by the number of users per car. So our revenue and cost analysis came together to determine the profit per user per year, which is demonstrated in this table. And we also excluded a couple of the car sharing options like joint transportation or joint ownership because those don't really apply to a car sharing company. So I'm going to turn over to Margaret to finish up.
Now this table shows the revenue, but to find total profit, we have to take into account population density. Because if a city has higher population density, there'll be more users within a certain zone that are able to use the car sharing service. Now for the 4 cities, the median income of each of the individuals are within $6,000 of one another, so we assume that they have relatively equal income distributions. Users for whom user price will be lower for car sharing than public transportation will be very incentivized to switch to car sharing services. For our profit equation, we assume that therefore there is a proportion K of individuals that will be incentivized to use car sharing services. And our profit equation then becomes the difference between revenue and cost times population density times K. And then using the values for revenue and cost that we found earlier, we can find the profit for each city and add it to this chart. The red values show the most profitable options for each car sharing option in each city. Thus, our final recommendation is that a company should develop a free-floating model in the city of Poughkeepsie, New York. A few drawbacks of this model include that we could not find sufficient data to account for the differences in income distribution. In addition, we did not account for the price of a jockey for one-way car sharing services that might have to drive the cars back to a needed location. Also, we did not perform sensitivity analysis due to running out of time. Furthermore, as Nancy said earlier, we have not accounted for personal preferences that might make people in lower income brackets much more likely to use car sharing services. Next, in part 3, we were asked to incorporate the new technologies of self-driving cars and alternative energy vehicles into our model for part 2. We made the key assumption that self-driving cars can be considered like one-way models because the cars could drive themselves back to any needed location. For this reason, we used the pricing model of the free-floating system Car2Go. For scenario 1, the lines again did not intersect, and public transportation was the most feasible. However, for part 2 and part 3, only for high salaries were self-driving cars the best option. However, for scenario 4, self-driving cars turned out to be one of the most cost-effective options across the board, which would lead to higher usage and thus greater profit for the company. Unfortunately, when alternative energy vehicles were held up to the profit test, they did not take the lead because alternative energy vehicles often must spend up to 60% of their time charging and thus do not spend their time being profitable for the company. A few limitations of our model is that we did not consider the fact that right now it is not feasible to have self-driving cars and a lot of alternative energy vehicles because they are very expensive. In addition, however, over time, they will become more cost-effective and thus will move solidly into the limelight of the car-sharing market. I'll now turn it back to Daniel to conclude.
Overall, throughout our model, we've striven to be specific. We've used a large data set and used several location and case-specific factors to make our model more accurate and more useful to consumers and companies wishing to evaluate car sharing in their location. Car sharing is an excellent method of transportation, and as the future comes, it will only be more viable. Lastly, we would like to thank the Moody's Foundation for funding this competition. It has been an excellent chance to try mathematical modeling, and we'd like to thank our coach, Dr. Olson, for teaching and helping us. Thank you so much.
Okay. Can you pull up your profit equation? I don't see fixed costs in that expression. Did you ignore them, or
The fixed costs for each company, how they price like monthly fees and such, or?
just what would be the fixed cost for doing one of these ride-sharing options?
So you can see they have monthly costs. So some, like Zipcar, has a monthly fee to be a member. So that's represented by MC, and that's, of course, times 12 since it's monthly cost. And then sometimes they have an initial price to join, and so we used an exponential growth. We have found the exponential growth of car-sharing industries, so we found that 12% of users are new each year, so this would be the percent that would pay the initial fee to use the car-sharing service. And so that's accounted by the first two terms in the top equation.
No, I was looking, you had an expression earlier. So you can go back earlier. Keep going. Oh, wait. Now you went to profit. Okay. You have revenue minus cost, but your cost didn't seem to include fixed costs.
Like maintenance, or?
Oh, well, you have all those cars you have to buy and things like that.
Yeah, so can you move back to the cost one? It's on the same page as the revenue one. It's forward. So CM car maintenance includes the cost of the time they're going to have the car. That's going to include the initial price to buy the car distributed over the years that you own the car.
Okay. All right.
Sure. Yeah.
Back to the very first, the traffic factor equation. Can you explain how you decided on that form, and is that supported by the data in particular? Is that a good fit for the data that you have?
So we decided to use an exponential form because of the constraints we tried to place on the model. We realized that as traffic increases to without bound, you're going to have a kind of standstill. So it's not going to increase linearly and hit like a peak point. Or sorry, it's not going to increase linearly without bound or in a fashion without bound. So we decided to place it like that. We also found that our model was somewhat, like some of the points were tending to move kind of in a square root fashion or in an exponential fashion. So we tried to shape a model around that in that fashion.
All right, and I have a question for you too that is about question 2. And in particular, you presented your 4 different scenarios. My question was, how would a rideshare company prepare for each of these scenarios, or maybe even self-identify in terms of where they fit in the scenario world?
Sorry, I couldn't hear the first part of your question.
Oh, okay. So how would a rideshare company, for example, figure out where they live amongst the 4 scenarios that you identified?
Well, we have the chart for the various models. So if they're a certain kind of car sharing company, they could use it's the one with the red values.
Mm-hmm.
It's at the beginning. So forward, forward, forward. So they would use if they're a certain kind of car sharing company, they could figure out based on that which one of the cities would be best for them.
Also, this is something that we didn't really take into account within the 14 hours, but each city could potentially, each city and each car sharing service could potentially identify which kind of niche they fall into in terms of what they want. So it's up to the company and which city they decide to invest in, I guess, like which category they would fall into.
Okay. I think we're good. Thank you very much.
you.
Thank you.